Alright, hey, welcome to our super awesome assignment number 2. I'm Sean M, 100412327.
Daniel Munasami, 100552012.
I'm Ivan Fedorov, ID number 100631299.
Alright, and then we're going to do this one a little bit differently. We're going to split off individually and record each of our own sections independently and then mix them all back together at the end. So, enjoy!
Okay, welcome to our assignment 2. I'll just be giving a brief rundown of our scene. So we did our assignment 2 in Voxel Engines. So how we came up with our scene is we auto-generated terrain with voxels, so it has that nice look, like it looks like Minecraft. We just voxels and auto-generated terrain. We got our deferred lights here, as you can see, our rotating camera. Let me stop rotating, and we can also move and control our camera. So this is our basic scene, and now we'll go into explaining the G buffer.
Alrighty then, so I'm going to be covering G-buffer generation and the math behind the actual lighting calculations. So if you watched our previous video on how deferred rendering works, I believe it goes over it a little bit. We'll go a little bit more in depth this time though. So basically the big idea with deferred rendering is that we basically defer, or we make our lighting calculations happen later in our pipeline after we've already drawn all of our geometry. So the big upside to this is we only do our expensive lighting calculations on pixels we can actually see. So basically, how we do this is we use render targets with multiple textures bound to them. So basically, with our system, we have our albedo texture, which is just the raw color data. So this is actually where texturing takes place in our system. So basically, this is just like the underlying color of the object. You can think of it that way. We also have a normals buffer. This is in view space. So like as you can see, as the camera rotates around, most of the faces have the same color. So basically, all of these normals are pointing towards the camera, so they'll have a similar color. We also have a view position. This is your position in view space. You can see that there's not a lot of blue in here like you would expect. That's because the view position is negative. So basically, the smaller the value, the further away it is, just due to how projection matrices work. And there's also a depth buffer, which is required for depth rendering. We don't necessarily need a view position buffer. You could reconstruct a view space position from depth and like a screen space coordinate, but just for simplicity's sake, we decided to do this. Use the view position buffer. It is a fair bit more expensive. It's an extra 3 floats per pixel, and we're using 16-bit floats to try and save a little bit of memory, but it is still fairly expensive. And if we could reconstruct it easily, we would have done that. But we just did it this way for time's sake. Yeah, so one other important thing to note is you'll notice that the normals are very bright. Basically, what this is in order to pack a normal, which can be from -1 to +1, into a 0 to 1 texture, we have to pack it into our 0 to 1 range. So basically, 0, 0 would become gray, 1, 1, 1 would become pure white, 0, 0, 0 would become pure black, kind of thing. And then we have to reconstruct it on the other side then. So actually, we can look at those shaders. So let me bring up. Let's just do a forward shader that supports normals. And let me actually open this in Sublime so we can get a little bit of syntax highlighting so it's not as terrible looking. Alrighty then. So as you can see, where we output to 3 different targets, this is our forward pass. So this is where we're generating our G buffers. You can also notice that we're not explicitly binding a output texture for depth. That's handled automatically by OpenGL. We don't have to worry about that. So if we go down here, oh yeah, we're also doing some tangent space normal mapping in a fragment shader, which isn't exactly the best of ideas, but I still haven't gotten around to updating our geometry generation to support tangents. So that's in the pipeline because this is super expensive to be calculating per pixel. But yeah, so basically, if you look here, what we're doing is we're taking our input normal, we're renormalizing it because the normals from the vertex shader are simply interpolated. We want to make sure that they're normals so that we don't have to do any normalization in our post-processing shaders like our accumulation or our lighting or anything like that. And you'll notice that we're multiplying by half, which is just 0.5, so that instead of 0 to 1, we're now to 0.0 to 0.5, and we add half, so that basically gives us our offset. And then in something like the point light shader here, this is the one that actually does our lighting calculations. We have the get normal, which basically does the reverse. So we subtract half and we multiply it by 2. So this could be a divide by 0.5, but multiplies tend to be a little bit faster on GPUs, so that's why it's implemented like that. Actually, this is a good idea. This is a good time to go over how our lighting works. So let me bring this guy back up, and we'll switch back to we'll go to deferred. So as you can see, there's a whole bunch of lights in our scene. We can also animate them and have them move around. Right now they're all just moving on a flat rail kind of thing along the X and the Y direction. So basically what we're doing here is we're using 2 separate buffers, because if we think about our lighting calculation, like our basic Phong calculation, actually let me see if I can bring one up here. Alright, sorry for the break there. It took me a while to actually find a good example of this, but basically a normal Phong model would look something like this, right? Where we calculate our lighting values and we multiply them by the object color. So if we do that calculation for every single light, that's going to be a little bit messed up, because really, if we think about it, the diffuse and specular components are per light source, right? Whereas ambient and object color should only be applied once. So we want to have a post-processing shader where we can accumulate our diffuse and specular components per light, but ignore object color and ambient. So how we're doing this, and we're actually using one extra buffer, which is a little bit of an annoyance. But we have our diffuse and our specular buffers. Really, we could get away with using one buffer. This was just to give us a little bit more flexibility over our lighting, so we could like do things like turning up and turning down our specular components. More just for control than anything, but we probably are going to remove it and replace it with a single buffer in the future for performance. So basically what we're doing in our lighting shader is we're simply calculating our diffuse, and instead of directly applying it with like an object color, like an albedo color, actually the only reason we get albedo is to get our alpha out. We simply just store the result of our diffuse and specular calculations. And then what we do is once we have these lighting accumulation buffers, like these two here, what we can do is we can mix them back in with our albedo to get our final result before post-processing. So this is our combination shader. So basically what we're doing, we're getting our albedo, our diffuse and specular, sampling them and mixing them together, and it looks like I am missing a bracket, or there's a bracket in the wrong place here. Yes, this should have been over here. Whoops, that doesn't look right. Anyway, I'll have to fix that later. Anyway, but yeah, that's basically the gist of that. So we can render a whole bunch of lights relatively performant. Although most of our time with lighting right now is sending uniforms across, so I'll have to look into that. I'm not sure what's going on there. And yeah, I think I'm starting to see some of the artifacts caused by that incorrect lighting equation. Let's see if we can do a live demo and fix that right up. That was in our lighting combination shader. Okay. So, specular.rgb. Because basically what we want to do is get our RGB component, add it to our diffuse. We're multiplying against 1. We're mixing against 1. Does that make any sense? Yes, it would, because we need white if we want to go pure albedo, so that does make sense. And we mix against 0, so yes, that would make sense. Alright, cool, so let's save this, and we'll reload shaders. There we go. So you can see the effect of the specular isn't as harsh anymore. And one other thing with the lighting, we also are using light foams. Let me get rid of all these. So if I change this guy to a cone light, you can see that the lighting is actually clipped by a cone shape. So basically what we're doing here is we're just rendering a mesh. We're doing all of our normal forward calculations in terms of matrix multiplication to get it in the right position. And then essentially our fragment shader will just only operate on these pixels covered by that mesh. And this is just using the point light shader. So all these super expensive operations will only happen on the pixels within this area here. So it's just a little bit of an optimization as opposed to doing a full screen quad, and lets us do some cool effects like spotlights. Alright, and I'll hand it off to somebody else to cover the rest of it.
Okay, I'm back. So now I'll be talking about how we did the light preparation, the dynamic light preparation in our voxel engine. So how it works is, first, let me bring up our lights. So as you can see, here's our lights. Let me give an easier look. So I'll clear all the lights that we have written from our file, and we can add lights in 2 ways, by clicking this button or by pressing the plus sign. So we'll start with 2 lights. And so how we prepare our dynamic lights is, first we start with an isosphere with 20 faces. From there, through each pass of tessellation, we divide each of the faces into 3 more faces. So basically we divide them and they look more, as you can see here, like a triforce. And then we do this until we get as many faces as we need. So in this case we do 2 passes. So 1 pass, we take one of the faces and divide them into 3 triangles, and we get a triforce. And then we do another pass, we do the same thing and get a more smaller triforce. So that is how we prepare our lights. As you can see here, we also can control our lights with the position. Let's make this one bigger so you can see it. You got some colors. It's green now. Or red. So yeah, that is how we do our light preparation with an isosphere. Send you off to the next part.
Ivan here. In this video part, we're going to talk about multiple dynamic lights and how we manage the movement for every dynamic light in our scene. First of all, let me demonstrate you a scene with one single dynamic light. As you can see, we have one dynamic light on our scene right now. And let me demonstrate you how we add a dynamic light with a randomized position, color, and volume. So if you press the plus button, you could see the added dynamic light in our scene. So let's go into the code and see what happens in the background. So this is our function for the input manager, key input. As soon as we press the equal or the plus button, we create a float value, a randomized float value for the radius, and we call the add light function from my world, which is our scene. The add light function adds a dynamic light into our scene with a pointer as a parameter. First we create the position. Then we create the color. And then we set the radius. And that's how we add one dynamic light in our scene with a randomized position and color volume. Now, let me demonstrate you how we load our dynamic lights using XML files. By pressing the Load Lights button, we get our dynamic lights by reading from the XML file we have. So let's take a look how that works. So this is the function where we show the button to load the lights from the XML file. This is our function that loads all the values for the lights, the position, the color, the type for the lights. First we create XML document by using TinyXML2 API. Then we find the node with the light. And for every light, we go through every element. But first, we have to create a temporary values that we could store the data and pass it to our add light function. So for every light in the XML document, for every node that has a light parameters in it, we take every attribute of it and put it into our temporary stores. Here we take the type, we find the attribute for type, and we take the value and separate them into the type, the mesh type of the light. This is where we fetch the position. This is the color. the radius, angle, and the Euler rotations. So for each element, attribute in the light, for each light in the document, we create a new pointer for our dynamic light, and we call the add light function to add the lights into our scene. We have to normalize the color as well. As you can see, we've successfully loaded 27 lights, and that's pretty cool. Let me now demonstrate you how we toggle our volume rendering. As you can see, we have 2 lights in our scene right now. If I press the key 2, now we can see the mesh of our dynamic lights. Let us go to the code and see what's going on. This is our function that handles the key inputs. As soon as the key 2 is fired, we call the toggle function, which takes a boolean as a parameter and the pool, and sets the boolean value to the opposite value. And in our main loop, according to the boolean, we set our rendering options, as earlier explained. Now let me show you how we manage all the dynamic lights, position, and movement. As you can see, we have 2 lights dynamically moving in our scene. Let us go to the code and see what's going on. This is our function that manages the dynamic lights boolean inside the GUI that we're using. We check if the dynamic lights is true. Then we go through all the lights in our scene, and if the number of the light is even, we move the light by the X value. If the dynamic light number is odd, we move it by the Y value. Show you how we cycle through different light meshes by using the key 7. As you can see, we have several lights in our scene right now, and we could render the volumes. Now I'm pressing key 7. Here you could see that the light mesh has changed to cube volume. By pressing 7 again, we cycle to the cone volume. So let us see what's going on in the code. This is our main function for input keys. As soon as the key 7 is fired, we go through every dynamic light in our scene. And change the volume type. Now let me demonstrate you how we toggle our accumulation buffer. By pressing 6, we toggle the accumulation buffer. Now let's look at the code, see what's going on. So here is our function that handles the key inputs. When the key 6 is fired, we change the render mode to lining diffuse. Then in our main rendering loop, we use the shader according shader for every light. And that's it.